Hello everyone, I'm Kanlei Zhou from Beihang University. Now, I'm in the second year of my PhD degree. It's my great honor to present our work, STGAE Spatial-Temporal Graph Auto-Encoder for Hand Motion Denoising. During the interaction in AR, human hand play a key role to perform operations such as grasp, move, and rotate. Therefore, accurate hand pose estimation and tracking can effectively improve the user's experience. However, the complex articulations, self-occlusion, and self-similarity of hands makes this task challenging, and prolonged interaction may cause fatigue and involuntary handshaking. Moreover, hand-object interaction in MR is extremely unfriendly for patients with motion disorders such as Parkinson's disease. Therefore, it is of the great interest to develop effective hand motion denoising method for addressing these problems. Cleaning motion capture data is the key process. Existing methods for motion data denoising mainly include traditional methods and deep learning-based methods. The former is done by modeling human prior knowledge on the feature and problems by different algorithms such as skeleton hierarchy and filter designs. The latter is done by deep learning frameworks such as CNN, RN, GCN, etc. Compared with the latter, the former is always depend on some priors and restricted by personal cognitive level. Existing methods are ineffective to learn the structured spatial-temporal patterns. For example, reference for roughly applying tremor to the hand as a whole ignores relative motion between joints. This work aims to propose a powerful framework for hand motion denoising, which can effectively extract spatial-temporal patterns with remaining structural constraints. Framework overview.
The proposed framework for hand motion denoising consists of 5 main parts. A is the corrupted data synthesis phase. B comprises the spatial-temporal graph construction and the STGAE. The constructed graph models the spatial dependencies between joints and the temporal continuity between consecutive frames. The proposed STGAE architecture learns a projection operator and a corresponding inverse one. The overall architecture is stabilized by a global residual structure. In the training phase, the joint losses are used to accelerate the model convergence. We evaluate models with 3 different metrics: hand pose similarity error, hand bone length error, and hand symmetric neighbor error. D is the graph convolution module with a self-attention mechanism. A self-attention mechanism is applied to learn which neighbors are trustworthy. The learnable part B learns the complete graph topology dynamically. STGAE consists of 10 basic blocks, 5 for the encoder and 5 for the decoder.
Data synthesis. In this algorithm, we simulate the abnormal hand motion by corrupting the hand joints independently to produce the corrupted data. During the data corruption, the structure constraints between joints are considered to simulate natural abnormal hand motion and preserve the bone length simultaneously. This is an example of data synthesis. A is the original data, B the shift matrix, C the occlusion mask, D the shift mask, and E is the generated data. Graph construction, neighbor partition strategy. The illustration of spatial-temporal graph. A is the spatial graph where the red circle denotes the center joint, blue circles represent the physical connected neighbors, and the cyan circles are symmetrically connected ones. B, the temporal graph where the red circle indicates the center joints, and the blue circles show its temporal neighbors of the before and after frame. Architecture, spatial-temporal graph convolution block. Due to the success of the stack hourglass network, the local-to-global scheme can effectively extract global features from graph-based data. We propose a novel spatial-temporal block with an hourglass structure. This figure illustrates the architecture of a basic spatial-temporal graph encoder block, where both the graph convolution layer and the temporal convolution layer are followed a batch normalization layer, a ReLU layer, and a dropout layer. Experience: robust denoising performance. This is a live demo of hand motion denoising using our method, STGAE. In this demo, the lighter shaded part represents the ground truth. As can be seen, for a deformed motion, STGAE works pretty well. Comparison with the state-of-the-art. We compare our method on the test set with the state-of-the-art method. Although all the methods perform well in most cases, ours achieves the best performance when processing extremely abnormal motions. We also compare our method on the test set with the state-of-the-art motion capture data denoising methods, and measure the above three metrics for joints across all the frames on the test set. Table 1 reports the detailed comparison results along with the inference time, training time, and size of the model weights. In Table 1, it is showed that the proposed method STGAE achieved better performance than the state-of-the-art methods. Experiments, ablation study. We perform ablation studies to investigate the contribution of different components of our proposed method. All the ablation studies are evaluated on the above three metrics: hand pose similarity metric, hand bone length metric, and hand symmetric neighbor metric. Table 2 reports results of ablation studies on tension mechanism. Both dilating B and C are not conductive to dynamically learn which neighbors are trustworthy. Table 3 elaborates the detailed results of ablation study on partition strategy. The removal of symmetric connected relationships still result in significant performance reduce, indicating the effectiveness of the proposed partition strategy. Experiments. The visualization of the trajectory, motion trajectory, and post-error curve plots. A, B, and C are the motion trajectory of the index tip on x-axis, y-axis, and z-axis respectively. The trajectory of the input, output, and the ground truth are colored in green, blue, and red respectively. D is corresponding MSE of the post-similarity curve, where the red line and the blue are the post-error changes of noisy input and denoised output. Compared with the input, the MSE curve of the output is almost flat and close to zero, indicating the huge power of our method. The visualization of the learned adjacent matrix. In Figure 6, a learned adjacent matrix heat map and its original normalized adjacent matrix are shown, where the colorful scale of each element in the matrix represents the strength of the connection. A is the original one for the synthesis dataset, including self-connections, physical connections, and symmetric connections. B is an example of the corresponding learned matrix. It is clear that the learned structure of the graph is more adaptive and not constrained by the physical and psychological constraints, which can give full play to the advantages of graph neural network. AR application demo. A demo of handwriting application in our skin. A is the control panel. B. It pause of beginning to write. C. It pause of ending to write. D. It handwriting of characters ISMAR and tremor, shown in bottom, and the corresponding denoid output, shown in the top.
Touch the tip of the left thumb with the tip of the left ring finger to close or open the control panel. Start writing by touching the tips of the thumb and index finger. Spread between the tip of the thumb and the index finger to stop writing. The bottom row is the original handwriting. At the same time, the top row shows the denoised output. In this demo, it is easy to see that the output in the top row is more fluent than the input in the bottom row. Therefore, it is verified that our proposed method is effective. Thanks for your watching.
That's all. Thank you.